Okay, check 1, 2. Welcome back to pre-algebra class. We have a little mini lesson today. Shouldn't be too long on the difference between fair games and unfair games. Okay, and we're going to start out with, it's probably pretty evident and pretty obvious that fair games are ones where the probability for winning is the same for every player. And an unfair game is where the probability of winning is different for different players or different participants, if you will. Okay? And that's probably about as obvious of a statement as you could get in 7th or 8th grade math. But they get a little more complicated sometimes. And we're going to get into some casino games and some betting situations here in a second. All right? So a game is fair if every player has an equal chance to win. So if two people are playing a game, player A moves one space if it is even. Let's picture a board game or something. Player B moves one space if it is an odd number. Which spinner would work to make this a fair game for the board game? Okay, and hopefully you are looking at the one that is red here that has the 1 to 6 spinner, because each would have exactly half of the numbers, or a 1/2 chance of moving. 50% chance, right? 50% of the numbers are even and 50% of the numbers are odd. So this would make it a completely fair game for both players. Okay. Courtney and Steve toss a penny 10 times. Courtney gets 1 point for each time it lands on heads, and Steve gets 1 point for each time it lands on tails. Is this a fair game? And does it matter that they're tossing it 10 times or tossing it 1 time? This is a fair game. All players are equally likely to score the same, so the game is fair. Now, that doesn't mean that it is going to be a tie. Just to be clear, this does not mean that it's going to be a tie. Courtney could land on heads 7 times, and Steve could land on tails 3 times. Just by chance in a small sample space, and Courtney would win, and Steve might be complaining, oh, that's not a fair game. But it was completely fair. You had the equal chance to, I guess, get points as Courtney did. Okay? And then that creates this interesting, does it actually matter that they tossed it 10 times? It doesn't. They could toss it 1 time. They could keep perpetually playing this game, and this game will still remain fair. Okay. Phil and Nicole placed 20 quarters and 8 dimes in a piggy bank. In turn, they shake up the piggy bank for a coin, and Phil gets 3 points for a dime, and Nicole gets 1 point for a quarter. And you might be like, well, that kind of makes sense. There are 20 quarters. That's a lot more than the 8 dimes. Right? So it makes sense that Phil's points should be skewed towards him. Is this a fair game or not? I want you to pause the video and think about, is this fair or not? Okay, and hopefully you had some time to think about this here. The Phil and Nicole problem. And this is the first one where we are taking a look at the points or the reward systems. Do the rewards make the discrepancies in the probability fair, or does it not? Okay, so let's analyze this. In the piggy bank, there are 20 quarters, and there are rewarding 1 point. Each of those would reward 1 point for Nicole. That means there's 20 points inside the piggy bank for Nicole. The 8 dimes in the piggy bank would each generate 3 points for Phil. So that means 8 dimes times 3 points. There are 24 points for Phil. So does each person have the same amount of points available in the piggy bank? And the answer is no. 24 is not the same number as 20. How could it be made fair? Well, you could basically do a whole other game, or you could skew the points in some way using common multiples so that they end up being the same. But usually what students say when we go through this problem is just put 4 more quarters in. Just put 4 more quarters, if you have them, into the sample space. or make this even in some way where the points would level out. Just put 4 more quarters in. It's about as easy of a way to make it fair as possible, right? So you can make it fair using your own creativity and discretion there. What about this one? Ryan is asking friends if they'd like to place a dollar bet on the outcome of a die roll. Everyone knows a six-sided die. If they get it correct, Ryan's going to pay them $3. Okay, if not, he will take their dollar. Okay, is this a fair game or is Ryan a hustler? Let's pause the video, see if you can figure it out. Okay, and welcome back. And suppose in this game you're playing with your buddy Ryan, and Ryan rolls the die and you say it's going to land on 5. Okay, well, what is the likelihood that that will happen? There is 1 5 on the die out of 6 outcomes, and that will generate 3 positive dollars for you. Okay, but every other outcome, would generate negative. You would lose your dollar. So if you continue to play this game perpetually, if you continue to play this game all the time, you're going to end up losing a lot more than you would win, or a significant amount more than you would win, right? So Ryan is basically like the carnival guy, or the guy at the fair, or he is like the owner of a casino, where they are strategically putting fun games out there for people to try to make bets on, to try to win prizes or win money, that they know that they, in the long run, are going to win more money than the participants would. So this is an unfair game, right? Another way just to do this with our probability skills is you would win 1 time out of 6 rolls, theoretically. And multiply that times the $3 of rewards, creates 3 positive dollars every 6 rolls in the sample space. And you would lose 5 times. You would lose 5 times every 6 rolls, theoretically. And each of those would generate $1 of loss for you. So 5 rolls times, 5 wins times a negative $1 is you would be losing negative $5. Are you losing $5 every 6 rolls? And you see that in this little pictorial I just drew right here. How could it be made fair, though? How could it be made fair? So in this case, we need to have the winning money equal the losing money. So really quickly, to make this fair, I'm not going to change his game any like I did on the last one. I'm just going to simply take that $3, the rewards, and heighten it up to $5. It can be made fair by winning $5. Now let's see. Right at the end, we would have $5 of positive money in the sample space, and we would have $5 of negative money in the sample space. Let's get a little more complicated now. Last casino game, there's 50 numbered cards in a deck. This is not a standard deck. There are 10 pink cards with numbers on them 0 through 9, 10 black cards with the 0 through 9 on them, 10 blue cards with 0 through 9, 10 orange cards, and 10 green cards with numbers 0 through 9. The participant plays a dollar bet on a number and a color. You pick a number, you basically pick a card. And the dealer will shuffle them and draw. If you get the card exactly, they both match, participant gets 7 positive dollars. If the participant guesses the number correctly, they win $2. The number, so if you guess the number, you get $2. If the participant guesses the color, you get only the color but not the number, then they win $1. Ooh, this is a little more complicated of a game, but it seems like something that like some people would want to play. What do you think about this game? Pause the video, see if you can analyze it a little bit. All right, so let's do this together here. If both match, you pick the card, the participant gets $7. And remember, there's 50 of them, so there is exactly one card in 50 that will get the participant $7. So that would mean right now $7 for, I guess we'll call it a match both. Okay? And one card. There are, I guess if we think about this critically, there's one card that would generate $7, and there are 9 more cards, 9 other cards out of the 50 that would match the, hold on, that would match the color. 9 other colors that would match the color times $1, which would be $9 for matching the color. I got lost in this own problem here. And then there are going to be 4 cards remaining that would match the number that you picked. Four cards remaining. So there's one that's a perfect match. There are 9 that have the 9 other ones that have the right color, and there are 4 remaining cards in the deck that have the number with the match. So you would have $8 in the sample space. That match the number. Okay, and if we add up these rewards, you would find that there are $25 of positive rewards. Does that mean this game is fair? Does that mean this game is fair? Here's what I want to ask you, though. How many positive outcomes are in the sample space? We have 1 card, 9 cards, plus 9 is 10, plus 4 cards. There are 14 winning cards that you are looking for. 14 winning cards. How many are losing? How many are losing outcomes? Remember, there are 50 in the deck, and hopefully you did a simple subtraction there to find that there are 36 losing cards. That would generate, obviously you lose your dollar every single time. That would generate negative $36. So is this a fair game, even though it seemingly was posturing like it could be a fair game? This is not a fair game. Okay? And this is sort of how casinos and carnival games work, right? They make it fun. They make it a little bit interesting. They have someone who's a host with a lot of energy. But in the long run, as people keep playing, the house or the casino or the carnival is going to end up getting more money than their participants would. And hopefully that's a little insight on fair versus fair games. See you guys.